enjoy your talk, actually.
Well, thanks for inviting me. Sorry I had to come on such an inopportune day. I'm going to talk today about two related projects I've done. So information theoretic looks at increasing robustness and adaptivity for sort of next generation wireless systems. And so the second part of this talk is work with my group mate Krish Eswaran and Anant Sahai, Professor Anant Sahai, and everything is also jointly with my advisor Michael Gastpar. So feel free to ask questions. Sometimes I think maybe some of my slides might be confusing. So if anything's unclear, just stop me. So what do I mean by these next generation wireless systems? It's helpful to think about the way we organize wireless systems right now, which is centralization. That's sort of the dominant paradigm. And the centralized planning comes in two sort of forms. One is physical planning. You can, as a system designer, you can decide where to place your base stations and how to physically organize your network in order to minimize, say, interference across cells. The second thing on the other side is the centralized allocation for spectrum licenses and exclusive licenses for spectrum, so that if you auction from the FCC a certain band, you're guaranteed, with the force of the law, that people aren't going to interfere with you. They're required to have good enough bandpass filters that they don't leak over into your allocation. So centralization is really good. It gives the system designer a lot of control over how to organize their entire system, and also a lot of control over outside signals interfering with their system. Unfortunately, it's led to an underutilization of the spectrum resources. So at Berkeley, we like to flog around. There's this thing that was done at the Berkeley Wireless Research Center where they stuck up an antenna and connected it to a wideband receiver, and just look to see how much of the spectrum is being used in downtown Berkeley over the course of the day. And it turns out less than 70% or something was not being used. So this means that there's a lot of available bandwidth, if you like, to support applications which can in turn make a lot of money, but it's not being used right now. So why is there money in this? There's money in this because people really are gluttons for wireless services. In particular, the advent of peer-to-peer is very attractive. And if you can find a way to commercialize peer-to-peer, you can probably make a lot of money. So users want peer-to-peer. They also want to be able to download rich content. It's not just text messages and so on. They want to be able to download TV episodes to their phone and watch it on the train. The third thing is that they want their connections to be ubiquitous. Doug and I were just talking on the way. I was at Cornell earlier this week, and I was on the fancy bus to go there, and there was wireless on the bus, so I could check my email for the 5 hours while I was driving to the middle of nowhere in New York. But, it would cut in and out. And so wouldn't it be nice if we put like 802.11 stations all the way along the highway or something, and it did a nice handoff, and as you were driving along the bus, you would just have seamless connectivity? That's what people want. People want to be able to do this.
Did you check your rate?
It was slower than DSL by a lot, but not that bad. I mean, it was like being in a very heavily congested cafe. Only I wasn't a very heavily congested bus, but I was getting rates as I was in a heavily congested cafe.
Do you know how many people were using it?
I mean, I watched a YouTube video, so yeah, about 7, I think, people at most were using it. And I could watch something on YouTube, so that was good for me. I was less bored. So, how do we enable these things? The way to enable these new systems is through decentralization, or at least this is what we like to tell funding agencies. And decentralization happens, again, both in space, where you have a decentralized network which may not have this access point user model, and also through spectrum licensing. And the FCC just concluded I don't know if anybody else saw this, just concluded the auction in the 700 megahertz auction, and they made something like $19.1 billion on this, on the TV bands, which is, I think, more per megahertz than any other spectrum auction in all of history. So clearly, there's a lot of commercial interest in reusing new spectrum. Well, random access is good, right? This limits the need for centralized synchronization. So again, decentralized. Huh? Right. And this is a very long service time queue, so it'll be like a very long time before everybody leaves. So these new structures, this new decentralized structure is going to create new challenges, and new challenges all the way down the line from systems type stuff down to theory. And so what I'm going to talk about in this talk are two particular challenges, I think, that addressing the particular problem of interference management in these kind of systems. So let's look at two example technologies that fit within this new decentralized framework. One is, of course, ad hoc and sensor networks. So you have a bunch of nodes in a network, and they're sort of self-organize themselves into a network, and they're trying to transmit data that they're sensing, or maybe this person is trying to download a file from this person over the network. So two key challenges in these kind of networks is robustness, and particularly robustness to malicious parties who may be operating in the network. They may have downloaded a virus, and they may not behave well with respect to the protocol. So, or just people who are eavesdropping and trying to inject false traffic into your network. So this kind of robustness is important to address. And another thing is, of course, adaptivity, because the link quality varies widely over space and time due to issues such as mobility and shadowing and other effects. So you want to be able to adapt to whatever the link quality is, in addition to, and also protect against, have some sort of robust guarantees on traffic. Another key technology is cognitive radio, which also been getting a lot of recent research attention. So in cognitive radio, you have these secondary systems, these cognitive systems, which are allowed to transmit as long as they don't interfere with the primary, but they may still be subjected to heavy interference from the primary. So you might be losing, even though you're allowed to access the spectrum. You might still be losing. Cognitive radio, of course, is enhanced by the development of wideband software radios, which can sort of look very widely across the spectrum and maybe find a hole in which to transmit. So you can sustain, by hopping over many bands, you should be able to sustain, some actual application of interest. And of course, cognitive radio is an important area of research for sensor networks in the sense of in municipal environments. You might imagine sticking a sensor network over the tops of buildings to detect the availability of spectrum holes for a cognitive radio system. And there were actually some talks at CISS on this, some of which are pretty interesting, I thought. So in cognitive radio, the challenge is, of course, the big challenge is this coexistence constraint. When lots of people have been doing work on even just basic estimation theory of can you detect the primary licensee? But again, we have these two other challenges: adaptivity, because the particular medium that because the cognitive system is hopping bands, its medium is changing rapidly over time, and also we have this robustness issue because of trying to protect against interference coming from other systems. So you see, this robustness and adaptivity are basically the two things that need to be overcome in order to enable commercial applications in these kind of frameworks. So how do we model communication channels? Well, I do information theory right now, so we use a standard. We open up Cover and Thomas and we say, okay, how do we model communication channels? And here it is. You just have an encoder which takes a message, maps it into a code word. There's a discrete memoryless channel. You get some code word receive signal at the output, and then the decoder tries to guess what message was transmitted. This is a great model. This is a great model that's yielded a lot of great results for the last 60 years. But it makes a basic assumption about the communication environment, which goes back to this idea of centralization. And that's the first of these is that interference is time invariant. And by that, mathematically, I mean stationary and ergodic. And so you can sort of treat interference like noise. You just have maybe you have a little bit of distributional uncertainty about the noise, and then you just assume that it's Gaussian, and Gaussian is the worst noise, and so you're you're happy. But this time invariance is like it's a biggie. It's the stationarity assumption. And the other thing is that users know distributions are various aspects of the channel characteristics, ahead of time. So they know quite a bit about what's going on in this box. Now these two assumptions may not hold in these new systems that, yeah?
When you say users and all these things, you seem to be modeling this as a single user.
Yeah, this is a single user link. In fact, throughout this talk, I'm going to abstract things away into single user links. So this user knows, for example, this channel matrix.
So where is interference coming from?
We'll get to that in a second. So if you assume the interference is like noise, you just assume that there's some mysterious interference signal which is modeled like noise and gets folded into the transition matrix given by this W. That's like this could be a BSC or a BEC or something like that. You just assume the interference acts like more noise.
Oh, I want to make a comment on the worst case noise. So only when your input is Gaussian, the worst case noise.
Yes, that's true. That's a saddle point. Yeah, exactly. But what I'm saying, among all channels with the same second variance, second moment constraint on additive noise, Gaussian gives you the lowest capacity. So if you plan for that, then you would choose Gaussian inputs again. So it's a saddle point. So what these two assumptions let you do is design codes which hinge on averaging the channel behavior over time. You let the block length grow very large, the channel behaves essentially deterministically, and then you design a code for that asymptotically deterministic channel. In this talk, I'm going to discuss a model where I explicitly put in the interference, if this addresses your question, where's the interference? The interference is going to be an auxiliary input to the channel. But I'm going to make as few assumptions about this S as possible. So in particular, I'm going to assume that in order to make some robust guarantees on achievable rates, I'm going to assume that S is chosen either by an adversary who knows quite a bit about your communication system, or is an individual sequence that's simply unknown, could be anything but is unknown prior to transmission. So that would be an individual sequence model. So in the first part of the talk, I'll talk about this arbitrarily varying model. In the second talk, I'll talk about individual sequence channels.
What about the knowledge of S and receiver?
If there was, so we'll see in the second part, if you put in some training in the, training or rate pilot information in X, the decoder could estimate something about the empirical statistics of S, but S has no statistical description, and there's nothing known to the decoder except for maybe we'll see a certain cost constraint on S. So you just assume that S isn't so bad that the capacity is 0, for example. Does that make sense? Did that answer your question, or?
So S is also not known at the transmitter.
It's not known at the transmitter, no. It's not a dirty paper coding kind of setup. This is S from some other system. Okay. So, and like I said, we're going to require performance under worst case assumptions on S. So we need to be good against all possible S. So the basic question is, how can we use extra system resources to help improve robustness and adaptivity? That's the name of the game. And by extra system resources, I mean, in particular, we're going to look at common randomness or randomization. If the encoder and decoder share a secret key, they can randomize their encoding strategy and therefore maybe get around some of the adversarial nature of the state sequence. And this randomization can be available at the application layer. So this is a kind of an example, a sort of rather simple example of a kind of cross-layer design where you leverage resources at a higher layer in the stack to enhance error correction actually at the physical layer. The other thing I'll discuss is feedback, and we'll see. I'll describe a scheme in which we use some forward channel estimation and feedback to enable an opportunistic communication over an individual sequence channel. So these are the two parts of the talk. So here are the 2 parts of the talk, and I guess I'll talk about the first thing. If anybody has any questions before I start, or I can just move. Okay. So I'm going to tell you a little story. It's a very sad story. Alice is going to writes a message for Bob in a coded letter, like, let's meet for dinner at 7. Alice entrusts the letter to her friend Spike, puts it in an envelope, gives it to Spike, and says, Spike, can you please take this to Bob? Spike, on the other hand, is not so friendly, and he opens the envelope and looks at the letter. Maybe he doesn't understand all the contents of the letter because it's coded, but he can still make some editorial changes. And then he puts it back in the envelope and hands it to Bob, and then Bob shows up at the restaurant at 9, and Alice thinks that Bob has stood her up and is very sad, and there's a misunderstanding that's gone on here. So the question is, what does this story have to do with ad hoc networks? Well, Alice could be on one end of the network, and Bob could be on the other end of the network, and Spike essentially could be the entire network in the middle. And normally one model for this kind of ad hoc network would you just model each link as an independent erasure channel with different erasure probabilities based on how strong the links are. And these erasures are caused by just random channel noise, or the interference you also can assume is noise. But this model isn't robust if you have an internal node which is untrustworthy. So say half the traffic that goes through here is tampered with by Spike, who injects fake packets instead of just erasing packets. So in this situation, you would like to be able to design a coding scheme that can defend even against Spike. So the question is, if Alice and Bob share a secret key, what is the capacity of this kind of setup? So let's abstract away the network part into just a point-to-point channel. And here's this arbitrarily varying channel model. So you have a key which is shared between the encoder and decoder, and you have this malicious jammer who can generate the state sequence for the channel. So we'll assume finite input in state and output alphabets, and we're going to assume, in fact, that the jammer has access both to the message that's being transmitted by the encoder and the transmitted code word. So this is quite a strong assumption. This can come from, say, the jammer in a wireless setting eavesdropping and has a better channel, so he can perhaps, could even possibly decode the message. But this is just trying to make our life as hard as possible, so that corresponding to the claims that you can make about achievability are as strong as possible. And I'm going to assume that there's a cost function on the state sequence, so that the jammer can't just do really anything, because if the jammer could do anything and this channel is structured in a certain way, the capacity could be just 0 all the time. Like, for example, the jammer could erase all the packets, and that's not an interesting case. So we just bound the some functional of the state sequence. Yeah.
What example? Just repeat that example for why the jammer may even know M.
Okay. Well, so mathematically, the reason that the jammer may know M is because you're trying to maximize the error over all messages M. So you might as well assume that it knows M, that it's choosing its strategy in the worst possible way.
I guess you're saying that x is a function of both k and m.
X is a function of k and m. So actually, from looking at x, the jammer may not be able to infer m, because the jammer does not know k. It knows everything else.
Is the secret key encoding already included in this picture, or that's yet to be added?
In the sense that it is an input to the encoder, it is added, but
so x is
a function of m and k.
And that's the secret function.
The function from m and k to x is known to the adversary. So that's like the code book is known, but k is not known. So it's like k is choosing a code book, if you like.
K is the key?
K is the key. And there are capital K bits in the key. Okay, is it clear?
So, can you please explain the cost function?
Okay, so for example, suppose the S acts to erase packets. Suppose it was just acting to erase packets. This cost function would say I can erase at most fraction lambda of the packets. The jammer can erase at most fraction lambda of the packets. If the jammer could erase any fraction of the packets, then the capacity is trivially 0. So we wouldn't be able to get anything through. So this is just one way of, at least the way they do it in the arbitrarily varying channel literature, one way of capturing a sort of constraint on how bad things can actually get.
Are you also assuming that given sufficiently large amount of information about M and X pairs, that the jammer will or the adversary will ultimately be able to figure out the code book?
It will be true in the construction that I present if you kept using the same key over and over again, and you sent every possible message M, then the jammer would figure out which K you used. And in fact, you don't even have to send every possible M. You can probably figure it out from fewer than that. But the assumption is that you use a fresh key for each session.
But maybe what the question is, can the jammer try to deduce the key from X?
Yes, if you design a particularly stupid codebook, then X will reveal everything about the key, and then you've lost all the value of the key.
No, but your problem is to find put achievable way to further not know the key.
Exactly. So I'm saying if you fail in that task, the adversary will learn everything about the key, and you will gain no protection from it. The case where there is no key is very difficult. I'll just put that out there. It's an open problem, in fact, finding the capacity for these channels in general without a key.
It's not that it can be arbitrarily zero.
No, I mean with this constraint, certainly not. But even the case where for some channels where there's no constraint model, but for certain channels it's just open.
So for K, capital K equals to 1.
For capital K equal to 0, I guess, 0 bits.
0, right?
Yeah.
Once you get to 1.
Yeah. So that's the deterministic coding setting, and the best result is from 1981 due to Chizar and Kerner. Actually, I was going to discuss. Oh no, wait. First, I'm going to discuss the error model. So let's look at. Randomized coding mathematically is just like I said. There's a family of codes indexed by secret K, the key K, and so the encoder is just a mapping from messages to keys, from messages and keys to code words, and the decoder takes the output and the key to generate an estimate of what message was sent. The interesting, the interesting thing about this model is the error model. So we're going to measure the error max over all the messages and max over all possible jamming strategies where the jammer knows both the message and the transmitted code word and can generate its state sequence accordingly. So it's the max over all these mappings. But then you average over the keys. And then it's the probability that you got the wrong message.
So the jammer looks at each for a big long code word. He looks at each. How does he generate the states?
So it will turn out that the worst case attack is a memoryless attack. He gets access to the entire code word acausally, or non-causally. So it's like you put it into the network, it's getting forwarded around, he collects all the packets, and he sees the entire thing, and then he generates his state accordingly. So it'll turn out that the worst attack is memoryless, and I'll show that in a second. I mean that's the result. So it's equivalent. If you're going to measure the error maximum over all messages, it's sufficient for him to attack actually any one message, because when you're measuring the probability of error, you have to measure it for that message as well. So if he attacks any message.
So you're saying that even if he knows it non-causally, causally it's okay.
If he knows it strictly causally, it's like a relay channel where he can only act on the current symbol without act on the current X. He can act on the current X only with access to past X's. That's the capacity is higher in that case. If he has access to the current X and can attack the current X, then the capacity is lower, and that's this model.
It just means that since he doesn't know the key, he tries all possible combinations and just take an average error.
I'm taking average over the keys.
All the keys.
Over the keys, because he doesn't know the key.
Are you using the key as a means for detecting or correcting errors, or are you also using it for authenticating that the message came from Anand?
The construction will use a message authentication code, like a crypto kind of message authentication code. However, it's being used for error correction and not to authenticate Alice. I haven't looked at the problem of people spoofing packets and then trying to do a substitution attack. That's also interesting. I think it would be more interesting when...
What Spike was doing here, example.
Spike's just altering the message.
Well, another way to look at it is Spike would just put his own message.
Yes, that is one strategy Spike could use. However, since because of this cost constraint, Spike can't substitute an entire new message in. This thing here. If Spike could put in an entire new message, that would be like saying, S completely substitutes all of X, and then, okay. So far so good. So this is how we measure error. It's a strong error criterion. So just to look at what the related work is on this problem, the first arbitrarily varying channel paper is from 1960 by Blackwell, Bryman, and Tomasian, and they looked at this strictly causal case. So the jammer has access to all the past values of X and all the past values of Y, actually, and can generate its current S with all the past information. So it's like a relay that hates you. And in that case, the capacity is found with randomization. Without randomization, the capacity is unknown, actually. And unknown under the maximum error setting, known in the average error setting. So the case without randomization was first studied by Sarwate and Wolfowitz in 1970, and then in this 81 paper by Chizar and Kerner, there is the sort of the best available rates right now. The construction that we're going to use uses list coding, and list coding was first investigated for these channels by Sarwate in a series of papers that were separated by about 20 years. And then this model is very much related to a certain model where instead of there being a jammer in a state like this, it's just got there's X and Y, and X and Y are subject to a distortion constraint. So the channel is constrained in the sense that it can only introduce a distortion D, and then it turns out the capacity is a rate distortion function. This problem was studied by Agarwal, Sahai, and Mitter at Allerton, I guess 2 years ago. So there's a preprint on archive, huh? No, it's just that the channel can do anything subject to a distortion constraint between X and Y. So the channel can output, you put in X, the out channel can output any Y that satisfies an average distortion constraint where you have some distortion function between X and Y. So a Gaussian channel is an example of this, only this time the noise can depend on X because it's measuring the distortion with respect to X. The most closely related work to this work is the capacity for these channels was found for bit flipping channels where S is just an additive noise sequence, binary modulo 2. And this is done in the theoretical computer science literature by Mike Langberg and Adam Smith. Adam Smith has a slightly different construction. So let's look at the scheme. So let's look at the rate that we'd like to target. So like you were saying, you're asking what the worst case strategy is. The worst case strategy is the jammer just connects X to S via a discrete memoryless channel U from S to X. And that U satisfies the cost constraint. And so it's just the max min of the mutual information between X and Y. So that's the worst, that ends up being the worst case attack. You have to defend against every attack, but this is the one that gives you, this is the one that yields the capacity expression. So the question is, how do we achieve this rate? Well, I guess the question is, what's the result? Or, well, how do we achieve this rate? So here's the channel model. Remember, the encoder and decoder share a key. So what they do is they just take the key in the message M and they pick a code word X. I'll describe how to do that in a little bit. And the decoder, what the decoder first does is it ignores the key and just list decodes based on Y. So it generates a collection of code words, L code words, which can explain the output Y. So it has this list of explanations. But this list of explanations is quite special because of the encoding process. It has a property that, so each of these candidates is some X of M prime and K prime, corresponding to different messages M prime and K prime, and keys K prime. So only one thing in the list will have the correct key value. So in particular, in this case, is the blue one. So the decoder says, okay, so this thing in the list is the only one that is consistent with the information I have about the encoding process, and so I'll just output that one.
So is it list of size L?
That's a parameter of the code. I mean, it's a construction. I mean, L as opposed to what, 1?
I should have 2 to the K.
No. It's just they're not necessarily 2 to the K good explanations for Y. It just says I have an L. For each Y, I can generate. The property of the code is that I can generate L possible explanations. I guarantee that the correct one is in the list. That's the list coding problem. So this L is a parameter of the construction, if you like. And L can be much smaller than 2 to the k, like constant. So it just picks the one that's consistent, and it outputs that one. So the result is that we achieve capacity. This is the capacity of these channels. And the error decays exponentially fast in the key size. So if you let the key size grow with the block length, which it needs to do, then the error is, n times 2 to the minus k, I guess, over 2.
Is the capacity point a saddle point in terms of the strategies the user?
No, it is not a saddle point. We'll see, there's a plot or two to show that. This max min is not equal to a min max. That's because this min depends on this p in terms of this constraint. So as I change p, the set of allowable strategies shifts around, and it's not a saddle point. Max min is consistently lower than min max. Not all. I mean, not in every single case, but in some cases. In particular, in the bit flipping case, they're equal. In the bit flipping case, this is just 1 minus h of p. It turns out to be 1 minus h of lambda, where lambda is the fraction of ones or fraction of bits that can be flipped. So, in order to prove this result, we need to prove some new results on list decoding, and we use this combinatorial construction for the bit flipping case. So let's describe those two. So the list decoding result is that I can create a code for an arbitrarily varying channel which achieves within epsilon of capacity with lists of size 1 over epsilon. That is to say, and what I mean by achieving capacity is it achieves these rates, and by outputting a list which is guaranteed to have the correct code word on it, and the size of that list goes like 1 over the gap from capacity. So in order to prove this result, you actually can just basically start out by creating a code word of all the typical sequences, and then joint typicality decoding means you just you receive your y and you just output all the x's which are jointly typical with y, and there's 2 to the n h of x given y of those, approximately. And then so you can see that the ratio of these two is just the mutual information, which is the capacity. And then what you do is you just start throwing out these code words like probabilistic method style. You just throw them out until you can achieve constant list size, and this is the kind of approach that Sarwate took in '93. So the upshot really is that finite list size is sufficient to get within a finite gap of capacity. So L doesn't have to scale with the block length necessarily, and the list size grows like 1 over the gap from capacity. So the second part. So this is the first part of the strategy. The decoder first does list decoding, but the question is how do you do the encoding? So what you do is you take the code words that you get from this code construction, and you just throw them into a table, right? And it's a table of you take half the bits of the key, and those index the column of the table, and half the bits of the key are sort of taken away from this rate here. So you just put them in this table of this size, and so the new message index is across here, and the rate loss is only 1 over n times half the key bits in the key of this. So that doesn't tell you the encoding yet. I mean, well, that doesn't tell you the encoding because you don't know how to map the message in the key to a particular cell. So what you do is for each column, you partition the set of all possible keys into sets of k over 2 bits, indexed by k over 2 bits. So each column is a partition of the possible sets of keys. All right, which means that for a particular key value, it only appears in 1 row in each column. So this key tells you, okay, so for K1, for message 1 I send x3, for message 2 I send x7, for message 3 I send x22. So this gives you a code. This gives you a code book indexed by this particular key. Notice the code books overlap by quite a bit. So for the encoding, what we just need to guarantee is that the intersection between any two sets of keys isn't too large. Otherwise, the jammer will be able to infer which key you sent. And so, and the way to encode is you just pick a, you pick a message, and then the key tells you which subset, you look for which subset A, I, J has the correct key in it, and then you send that code word that's in that cell. So this is the encoding strategy. The way you generate this table, these A's, is just a combinatorial construction. It goes back all the way back to Erdos, and it's used in message authentication protocols.
Is FTK a function of the code rate?
It is not a function of the code rate. It's a function of the block length, however. So maybe it is a function of the code rate in that sense.
For this strategy, we need to satisfy n times IL, unless the term should be larger than 0. So,
It should be larger than 0, yes.
but it's independent of IL, it only depends on
It only depends on n. It can be made to only depend on n. Yeah.
I have a question. Maybe I didn't understand. But this encoding scheme is assuming that the adversary is doing that worst case.
No, this is not. This is not assuming the adversary is doing the worst case strategy.
This is true for any adversary.
Any adversary which has the knowledge that I said the adversary has, it knows the message and it knows the transmitted code word.
So that person need not do the DMC thing.
Doesn't need to do the DMC thing. Yeah, exactly. So this is universal in that sense.
Okay, then I was thinking
No, it's that's why max. If max min was equal to min max, then maybe you could plan for you'd say, oh, the adversary is using the strategy. I will only protect against this thing but that's not the case. So the error trade-off, as I said, was exponential in the key size. So this scheme has a whole range of you can use it with a whole range of key sizes. So it's kind of nice in that sense, depending on what kind of resources you have available. So if you only have a very small number of bits of the key, if you have only O of log n bits of key, if k is only O of log n, then your error decay is only polynomial in n, which may be good for some applications, with very low rate applications, for example, but probably not for transmitting movies or something. So, but if you have n to the delta bits, you don't even need to have the same order, same number of bits as you're transmitting on the forward link in key size. I mean, if you had that much, that's a lot. But if you have n to the delta bits, you still get exponential decay in n to the delta. So that's a good. That might be a good regime in which to operate these kind of codes. So what's the upshot? Oh, sorry. So I have an example. So here's an example of a real additive channel. So it's just binary input, binary state, S, but the output is the real addition of the two. And so you can see here I plotted versus the input distribution the mutual information. So you can see you would want to operate, of course, at the top points of these curves. And you can see the capacity achieving input distribution varies as the constraint on the state varies. Another example is if the state is just picking between either your channel looks like a BSC or it looks like a Z channel. These are kind of cheesy examples, I admit, but they're easy to compute. You can see again the capacity achieving input distribution varies with the state. So it varies with the state cost lambda. So you get some weird behaviors in these kind of channels just numerically doing because of the dependence, because you can't just switch the order of the max and the min. So the implication of this whole thing I was discussing is that you can use security resources at the application layer to enhance robustness or error correction at the physical layer. So there are two directions you can think about going, I think, that are interesting, and maybe you may get some interesting results. The first is to use, since we use list codes in the code construction, there's been a lot of recent work in the coding theory literature on practical list codes for Reed-Solomon-like constructions for the list decoding problem by all these authors and many others actually. And so if you can take those algorithms and use them with soft information in more general channels, you should be able to add this randomization and then get a capacity achieving code that works in polynomial time, because these work in polynomial time and that list hashing works in polynomial time. So that's pretty exciting. There's another connection actually to, there's been a lot of work on, since we abstracted away the network into a point-to-point link before, there's been a lot of interesting work on coding theory for network coding and developing LDPC-like and Reed-Solomon-like code constructions and a whole framework paralleling standard coding theory and standard Shannon theory for network coding now. And this is exemplified in these two very recent papers by Krish Eswaran and Montanari and Urbanke. So these are two interesting directions I think that you can take these kind of randomized constructions and then together with practical constructions and then maybe hope to get robust codes that work in these kind of networks. So that's all I had to talk about this. And I'll go on to this feedback story if anybody else has any questions about this.
You just give a children a hill.
The converse is trivial because the converse, the adversary could always use that discrete memoryless attack. So that's always an upper bound on the capacity, and we just show that you can achieve it. So. Okay, so on to this feedback story. So what's the problem? I mean, what's the problem we're trying to solve? The problem is that the link quality, of course, that you have in a link like this may not be known ahead of time. In fact, it might be pretty bad. And if you plan for the worst, like and you do in an outage kind of setting, you'll get very great reliability if the channel is better. But the rate that you can sustain is not going to be commensurate to the link quality that you have. And so you'd like to be able to squeeze out all the juice that's left in that link. But this link is going to be subject to some sort of interference. So what's the problem? The problem is that the link is varying over time in an unpredictable way due to the fact that there are other interferers in your system that you don't have any control over. This is another communication system. So you can't schedule over it. And we want to be able to transmit as much data as allowed by the channel quality. In particular, if this guy is off, you still want to be able to get all the extra rate that you should get. And so we want to use feedback in a kind of hybrid ARQ setting, kind of like type 2 hybrid ARQ, to make the transmission adaptive. And so you want to try an information theoretic analysis of this kind of setup. So here's a simple model for the problem. Here's just, it's going to be binary modulo 2 additive. So this so X is binary, S is binary, and this is a mod 2 addition. And you have this 0 rate feedback link from the decoder back to the encoder. So what we'll assume is that the channel noise S is going to be some fixed individual sequence. We don't know anything about it. It's arbitrary. It's fixed ahead of time. In particular, I'm not going to assume that S is generated adversarially from X and M and that. That's not in this model. It's just something you don't know what it's going to be over the course of the transmission. But we have this feedback link, so maybe we can make things adaptive. So this problem, of course, has been studied, or variations of this problem have been studied by a lot of people. The one important work is this compound channel model by Chamkert and Telatar. You have a binary symmetric channel with unknown crossover probability, and the output Y is actually known to the encoder's feedback situation, and so this uses full feedback, which is not what we want, but it doesn't really use any resources in terms of common randomness. So the key size that's required is 0 essentially, and doesn't assume any state knowledge of the state ahead of time. So that's good. So blue is good and red is bad. It was also looked at by Stark Draper, Brendan Fry, and Frank Shishang in a related work, where they assumed that this BSC now has a variable crossover probability, PI, or PI over time is varying, but it's known to the decoder somehow, and uses 0 rate feedback. So here we have good 0 rate feedback. That's what we want. Again, the common randomness resources are negligible, or incredibly negligible. But for some reason, they make this assumption that the decoder gets access to this P. So we don't want that. The most related work to this work is by Ofer Shevitz and Meyer Feder, and it's pretty recent actually. It's still under review. And I show 2 feedback links here because there's conceptually 2 feedback links here. The encoder can track the output, which means it can basically knows everything the decoder knows. So you don't need this other feedback link, but there are 2 kinds of feedback information. So that's why I draw 2 here. So what it does is it does a forward tracking. The encoder is tracking the channel via the feedback link, and it runs a kind of modified Horstein scheme, which is like a same as like Skokvik-Kailath kind of feedback, classic information theoretic steering algorithm for feedback systems. Together with there's a lot of machinery that goes on here, and it uses sort of feed-forward training to inform the decoder of how good the encoder can track how good the channel is via the feedback. It also uses some sort of feed-forward link to tell the decoder how good the channel is as the whole scheme goes along. And so the decoder can also then sort of track the channel and then can decide when to decode. So this is a variable block length scheme. This uses full feedback, which we don't like. But it has, again, bounded common randomness resources, and there's no assumption about the state information being known to the decoder or anything like that. And this is an individual sequence model, so there's no BSC either. So in this work, we're going to do two things. We're going to, again, use some sort of feed-forward training to allow the decoder to track the channel. And we're going to use a randomized code construction using this key that helps overcome this individual state sequence problem, regardless of what it is. And so our scheme uses 0 feedback rate and bounded amounts of common randomness and doesn't assume anything about the state information. So what's the target, right? So the target, what I mean by, it achieves the capacity or something like that, well, there's some empirical frequency of 1s, there's empirical weight of the noise sequence, right? And we're going to try to get 1 minus h of that empirical noise. That's what we mean by capacity. That's sort of, if it was a BSC with these statistics, empirical statistics, that would be the capacity of that channel. So our goal is to achieve a rate close to this for most noise sequences S, that is, this P amp depends on S. So for most sequences S, and then with high probability over the randomness in our scheme.
So you design the code and the keys strategy.
Yeah, it's more like designing the ARQ-like protocol and how to design a threshold, how to design a codebook that works well with a thresholding strategy for decoding. So the result is that, oh, that's a weird symbol, that as long as the state sequence is not such that the capacity would be almost 0, so if it doesn't look like a BSC with crossover probability 1/2, essentially, within the small factor of that, we can achieve rates better than within a small gap from the empirical capacity, and all these gaps go to 0 as you let the n get large. So how do we do it? Well, you first divide up. What you do is you just try to send a certain fixed amount of information, k of n bits at a time. So you send k of n bits for a while. It's going to take you a while to send it. It depends on how noisy the channel is. So it might take you a short amount of time if it's not very noisy, and a very long amount of time if it's noisier. And then once that's successfully received, it tries to send another k of n bits. So you're trying to send pieces of this message, and you're trying to send as many of them as possible. So each time you send k of n bits, that takes one round, and the rounds are variable length. Within each round, you divide it into chunks or packets of fixed length. So in each round, you're sending a chunk, and you're sending another chunk, and then you send another chunk. And as soon as the receiver receives enough chunks, it can decode. And within each chunk, you randomly partition each packet into randomly chosen training positions, and the rest of it is just the code word positions. So the decoder can use the training positions to estimate the channel. So here's a snapshot of the scheme. It's easiest to see via a little flowchart. So the decoder is tracking how noisy the channel is. It's measuring how noisy the channel is, and it has two thresholds, whether or not things are too noisy, that is, it exceeds the threshold, or this other threshold which tells it that it should be able to decode. That the code construction is such that we can guarantee decoding. So the transmitter sends a packet which contains data and training, a chunk which sends data and training, and the receiver estimates the channel. So now it has some sort of estimate of the channel, and it asks itself two questions. First, it asks, are things too noisy? Have I crossed over this red line? The answer is no in this case. So then it asks itself, well, did I cross over the blue line? Should I be able to decode? And again, the answer is no. So it says, okay, please, I still don't know what you're trying to send me. Please send me another packet. So you do this, and it gets here, and still the answer is no to both questions. Still the answer is no to both questions. And eventually you get to some situation over here. one of two things can happen as this thing is looping around sending more packets, and the decoder still doesn't know how to decode. Things could be too noisy, could cross over the red line. In that case, the decoder says, you know what, on average, over this entire time period, the channel has been so noisy that it's not even worth trying to use this information. It's all garbage, just throw it out and start over. So start over. Otherwise, the decoders, if it crosses over the blue line, then the decoder says, okay, now I have enough information. On average, the channel has been not so noisy, and I have enough packets that I can decode. So I decode. And then start sending me the next round. So it's very, very straightforward. This is kind of the way, actually.
But why would you start over? It's already some information.
So imagine the channel was like a BSC 1/2 for the, you start up the scheme, and the channel is like a BSC 1/2. The capacity is 0, right? The capacity would be 0. It's just random noise. So you're estimating the channel, and after getting a certain, a few packets, you say, okay, this thing, based on my training estimates, it looks like this channel has capacity 0. If you can know that your estimates are good, then you lose nothing by throwing out those packets, because they're so corrupted that it's not worth continuing. You'll in fact only help yourself, because you've thrown out some noise sequences, some really bad noise sequence. Okay, so in each round we're going to choose a random codebook, and it turns out the number of random codebooks you need can be made small via some standard results. Well, it takes proving, but it's not too hard. For each chunk, we send 0 in all the training positions, so it just measures the number of bit flips that happen in the training positions, and that's how it estimates it. And then the rest of it's just a code word. So if you have the code word, and you sprinkle on top the training positions and then press them in, and then that's what you get in each of these guys. So the decoder strips out all the training and puts all the code word things together, and that's the overall code word it's getting, and uses the training to estimate the empirical channel. So if the things were too noisy based on this, then it throws out the package. Otherwise, it has to decide whether it can decode. And so what's the threshold that it uses? So it uses the training to estimate the empirical capacity of the channel. So it has some p-hat estimate of how noisy the channel has been up to now, and then it just calculates this mutual information. And if the number of bits that are trying to be sent divided by the number of channel uses that have been used to send it in the code word so far after the mth round is less than the empirical mutual information of the channel, then it can decode. So the guarantee for the codebook is that as long as the empirical rate is less than the empirical mutual information, then you're safe.
So you use this information to establish the threshold, whether it's decodable.
Exactly, whether it's decodable or not. And all the math, all the proofs are essentially around trying to around both proving that this codebook construction is good and proving that the estimates are good. So more generally, you can do this with a general channel with a general state parameter. And so the result becomes, as long as you fix an input type P, input distribution P, and as long as the empirical mutual information is bigger than something that is very small, tau is going to 0, then you can achieve rates bigger than the mutual information, the empirical mutual information. So that's a generalization of the result. So just two quick comments about what's going on here. There's not always a universal input distribution P, so you can't always achieve, in the general result, before I said for the binary, modulo 2 additive thing, you would get capacity. 1 minus h of P, that's capacity. Here you only get the empirical mutual information because P may not be universal. And you can see that if your channel is like somehow this Z channel controlled by S. If S is 0, then it's clean, and if S is 1, it's a Z channel. The capacity achieving input distribution depends on the empirical frequency of 1s in the state sequence, and so therefore there's no universal P that's going to work. Yeah.
Do you also get a bound for how far the empirical mutual information is from the true mutual information?
Yes, it's required in order to prove that the codebook is decodable. It's related actually to some results that are in Cover and Thomas on bounding the total variational distance and using that to bound the mutual information. But it's just algebra almost. The other thing is that we may actually do much better than the empirical capacity. Because of the fact that we're achieving this, we're achieving this low, this R is just, we're just saying that this R is bigger than this mutual information. We don't say that it's in fact also less than this mutual information. It could be better, significantly better. And that's because all we're doing is we're saying we at least achieve this lower bound. Here's the capacity in the dotted dashed blue line, and all we're saying is we achieve points on this red line. So in particular, sometimes we may achieve this point here, and sometimes we may achieve this point here. But if you look at what the overall rate you're getting is, you're basically time sharing the line between these points. And due to convexity, you might be achieving a rate here when the empirical capacity should be down here. So, in fact, the rates that you achieve in the scheme can be higher than what you would naively assume the capacity to be for these channels if you took it on, if you just coded over the overall block length, which shows that shorter time scale adaptation can be quite beneficial, especially if the channel is non-stationary, right? And that's sort of, we knew that, so it's good that it happens here as well. So the point is that this on-the-fly channel estimation, and again, as I said, shorter term variation improves the rates that you can get. And the feedback lets us adapt the rates to the actual channel quality. And this key size that you need, I didn't describe it, but the key size can also be made quite small. It's another result that we have, which means that if you have a control channel, if you're establishing this, doing this feedback over a control channel, if your control channel is good enough that you can do some of this handshaking, if the receiver and transmitter can do some handshaking at a little bit better than 1 bit per packet feedback, you can use more feedback to reduce the amount of a priori shared randomization that's needed. So just as a few statements about where one might go with this. So really the idea in these last two things that I presented is that we had these new applications, these new ubiquitous, going into Starbucks and starting to download last night's episode of Lost while you're getting your latte, and then walking out into the street and having it seamlessly continue downloading Lost. These new applications are going to require some decentralized architectures because, to support these personal user multimedia kind of things. And these decentralized architectures require better, more robust and adaptive coding strategies and protocols. And this requires new algorithms and new analysis on the theory end, so at the bottom layer. The current state of the art needs to be improved, I think. And so we saw an example of this as new applications to models and trade-offs in terms of this secret key paradigm, which is both used for, can be used for both security and error correction, and also this feedback story with opportunistic communication for time-varying channels. And in the bigger picture, one thing that's raised in the first part is this issue of security, the relationship between security and robustness. I know that a lot of work is done here on wiretap models. It's pointless to have robust. It's pointless to have robust communication that's totally insecure, but it's pointless to have totally secure communication that isn't robust to link variation, that isn't robust to modeling assumptions. So maybe there is a trade-off to be exploited there. And in the future, and I've already done some work on this, how collaboration between users, like you were saying, this has been mostly for point-to-point links, point-to-point link modeling. But collaboration can enhance adaptation, especially in this adversarial setting. You can look at intrusion detection problems for networks. That is quite interesting. And there are, along with this collaboration story, there's some questions to be asked about scaling log height behavior for larger networks scenarios, coexisting networks of, say, different densities. So that's all I had. So thanks for listening and asking me questions.
Any more questions?
So in your first part, so this transmitter and receiver, they share the key, right?
Mm-hmm.
So in order for the receiver to decode that, they need to synchronize the key, right?
They need to synchronize the key, indeed.
So how do you achieve that?
So they're it's not addressed in that particular framework. You just sort of assume that the key is there. There's been a lot of so there's information theoretic work on key agreement protocols. but there's that gap between information theoretic security and and computer science security, where in the computer science end you start making these polynomial time assumptions. In a practical setting, you would have to start making those assumptions on the adversary, which raises some questions, of course, about, well, it has all this knowledge, but and then you can say, well, now maybe I should design my code book such that, this mapping from message and key to code word is like a one-way function. If that's a one-way function, then again, the adversary shouldn't be able to infer anything about the key. But that would be for a practical, like if you, I mean, by practical I mean, a linear block code kind of approach to that problem. So if you could come up with good linear codes, then you could start looking at combinatorial properties of those encoding mappings.
So, Anand will stay for a few minutes, right?
Well, I mean, I'm around for a little while, so.
If anybody wants to talk further.
Yeah.
Thank you.
Thanks.
If you have a system that's a little different from that I'm not thinking about an adversary, but dealing with interference. Think about a pervasive sensor network,
Right.
where the messages are mostly known, but change only slowly.
Mm-hmm.
You're constantly saying, my temperature is so and so.
Right, exactly.
It's going to be a little different, but you have some knowledge of the set of answers where it's going to be. Can this help you handle interference in that situation and allow you to deal with more messages coming across? It can raise the effective capacity because you've lost some information because of the predictability of the messages.
I see what you're saying.
Looking for novelty. You're looking for novelty in messages.
Right.
Most of them are the same, but they still interfere.
Right.
The novel ones.
I mean, I don't think these protocols are particularly suited to that kind of question. I mean, I think you would.
Well, your attacker is just all of the other.
Your attacker, and I've looked at a similar kind of model for sensor networks where, all the other sensors transmissions are interfering with your own. But I haven't looked at that. Would be an interesting joint source, like sort of joint source channel coding, where instead in fact, you don't need to. You would want to. That's a very good question, actually. So you would want to actually encode novelties. In fact, you could probably do it via power control, actually.
Well, power control is expensive in little sensors.
It's true.
Right? You want to keep those parts as simple as possible.
Right.
You don't want to have to talk to them and say, oh, you're too loud, shut down. That means you have to have a receiver or a synchronized system or
Right.
something to do that. If they're just sitting there blindly giving out the temperature and you're looking for a novelty, disaster management people are looking
Right.
for things like that. Then you can imagine you've got I'm just sort of thinking of analogies, you've got that list of possible code words.
Right.
You've got a list of coding coming out, but I'm looking for one that's not what it has been.
Well, if you so you might be able to use a similar structure and have whoever's trying to listen for the new message. So the key then would become a choice of a particular special protected message. So the receiver first tries to do this procedure. If the list contains one of the special messages, then it'll flag something.
Then it can do more processing.
Otherwise, it's kind of, if the list contains if the list doesn't contain any special messages, then it.
And you don't want to have to communicate back to the sensor.
Right.
You'd like to have the sensor just sitting there giving out its messages, and every once in a while it says, ooh, something changed with me.
Right.
Then
it maybe uses the key as the fact that something changed,
Right.
or what changed in some way, and it uses a different encoding mechanism
right. And
to
the
generate.
encoding mechanism ought to be something that allows you to handle all of these conflicts and interference in an effective way.
Right. So basically you have two channels. One is when nothing is changing, and then one is when something has changed. And when something has changed, you would use this new code, and the decoder first looks for that. The receiver first looks for that the special code, and then otherwise it operates the other way, the standard way. That might work. Here.
In your second part, you said your receiver, you send the message one chunk. If the receiver couldn't decode that, you ask for transmitter to send another chunk. So this two chunks, the difference is duplicate that.
No, they use the
But
the
does
same. Essentially, it uses a prep each round.
Each round.
But within a round, it's just using.
It's in,
Yeah.
So when you're talking about cut that message into chunk, and that means it's a big code word and just cut
You're
it.
just sending more of the code word, more of the code
Okay,
word.
so it's kind of like a radius code.
Yeah, it's like a radius code. In fact, it is radius code. Yeah, just sometimes I use the word radius code talking to people and they don't know what I'm talking about. So I just started preemptively stopped using the word radius code when I talk to people.
It's confusing.
Because some people I guess either don't know what it is or they think it's a very specific thing. Radius codes are only found